we did titrations, right? Last time we did titrations. Now we are going to, we did more strong base, weak acid. Well, what about if we have a weak base and a strong acid? So one thing to identify every single time when you're doing a titration is, what should this curve look like? I'm going to give you a hint on your exam. I'm going to have you draw one of these curves, right? Just letting you know that's going to happen. What should your curve look like? That's going to help you determine where your pH should be. Like, for example, I noticed on a lot of people's quizzes, like their pH, you had a POH or you had a pH instead of vice versa, right? You didn't exactly know where your pH was supposed to be. Like, now what do I mean like that? So if you're starting with a weak base, well, your initial pH had better be greater than 7 because all you have is a weak base. Right? If you're before your equivalence point, again, your pH still has to be greater than 7 because you're still at a base. Now, when you're like beyond your equivalence point, now all you've got is your acid left, right? So your pH had better be lower than 7 and a lot lower than 7. So keeping an eye on what this curve should look like is very important. So you need to remember what you're starting with and what you're adding when you're doing these. So now, when we have a weak base with a strong acid, our initial pH, so we have I'll just read this. So we have 25 milliliters of a 0.1 molar ammonia with 0.1 HCl. So that means we're starting with our ammonia and we're adding our strong acid. So our initial pH is going to be determined by using the Kb of the weak base. So our overall reaction is this. So that's what we're doing. But this is going to break up into smaller pieces because initially this is all we have, right? And when you put a weak base in water, you get your conjugate acid and your conjugate base, right? And so I don't think I gave you, okay, yeah, there it is. There's your pKb and your Kb. So I would have had to give you one of these, right? For ammonia, I would have given you one, especially for your exam, again, because your exam is not open note and not open book, right? So I would give you a Kb or a pKb or a Ka or a pKa. I would have given you one of those four. So now this is what we've been doing, the pH of a weak base. We've already been doing that a bunch. So we've determined that's all we have in here is our weak base. So we just do our ice table, and I feel like everyone's good with these ice tables at this point. Right? So we have our X, we're going to assume our X is small, right? Here's our Kb. We need to remember this is a weak base. So we must use Kb in our problem, right? So it's going to be Kb equals our NH4 plus, right, over our OH, sorry, not over. Right, and then so we end up with our Kb is 1.8 times 10 to the negative 5. No. Ah. Sorry. I love my computer. Let me try this again. I just have to reshare the screen one more time. And I'm going to have to rewrite it over. That's okay. Okay. So we end up with 1.8 times 10 to the negative 5 equals, right, is going to be x squared over 0.1, because again, we're going to assume x is small. Ignore that. When we do that, we get x equals 1.3 times 10 to the negative 3. So what I noticed a lot of times on the quiz and the exam is people will just go, okay, well, what's the pH? And like they'll be like, oh, the pH is negative log of this. And they're like, oh, That's the pH. But this is not the pH. Because remember, this X here, this is OH, right? So this is actually POH we're finding right now. So keep your eye on that. A lot of times we just like kind of forget what we're doing, but you need to remember this is a base. So if you just did the negative log of this, you're going to get like around 3-ish. You should go, oh, I have a base. Something has gone wrong. I should have a number greater than 7 here. Okay, so when we do that, by the way, for your quiz, you still have to do your X's small. For your exam, if this was an exam question, what I would allow you to do is to do this. So you can either do, let me just erase this here. Now that we've been doing this so long, so this is what we get for our X. So you can either do this to prove your X is small, right? So it's going to be your X over your original concentration. That's totally fine. Or I'm okay if you say that, and you can literally write this, and you can say X is small works because the difference in magnitude between the initial concentration and the kV was 4, which our X is small will work. I'm okay if you want to write that down. I'm also okay if you want to just do the math. Whichever one works best in your brain is completely okay with me. Just don't forget to check your X is small. Okay, so when we do this, again, you could have done POH, KW, whatever. Anyway, no matter what you're going to get, I feel like we know how to do this now. We get 11.13. So again, weak base, only a base. This is just going to be doing the KB of a weak base. What to watch out for here? You have to use KB, right? Your X is OH, right? So those are things to watch out for in this first piece of your titration. Okay, the next piece. So this time we're gonna add 5 milliliters of HCl. So every single time when you do a titration, we need to know where the end point is, right? So that's a very important thing. Where is that equivalence point? So we know where our equivalence point is because remember, at the equivalence point, moles of acid equals moles of base, right? So when the moles of this equal the moles of this, we are at our equivalence point. Okay, so that means, now how can we tell where we are? So we're before our equivalence point, we're adding 5 milliliters of our HCl. So if we're adding 5 milliliters of HCl, hold on, I think I have a, did I give you key? Okay, good, I gave you your KB. You're gonna need this. Okay, so now, oops. How do we know that we are before our equivalence point? Here we are, here's the amount of HCl, here's our moles. Here's the moles of our NH3. So it's less than, right? So our moles of our HCl is less than our moles of our NH3, which means we are not at our equivalence point yet. We are before our equivalence point. So we have a bunch of base in our beaker and we've added some acid, but we are not at our equivalence point yet. So our answer should still be basic, right? Because we just added a little bit of acid. So we should still have a number greater than 7 when we're done. Okay, so this is the amount of HCl that we have added. Now, whenever you add anything, so in any of these problems that we've been doing, if it says something is added, mole table. If something is added to something else, you're going to have to do a mole table, right? And so when we do our mole table, we look here, and so we have our NH3, we're adding our HCl, and when they react together, they're going to make this salt. So if we have, our NH3, we're adding HCl, and when we put those together, we make our salt. I think I'm going to switch this around because I'm going to actually, no, it'll be fine. So that's our reaction. And so our moles before, so we had 2.5 times 10 to the negative 3, right? we added this much HCl. That's supposed to be a 5. And we don't have any of this, right? So now, Le Chatelier's. If we have our acid is gonna react with our base to make more of our salt. Okay, so when we do this, that means we're going to use all of our acid. It is going to react with our base. When it reacts with our base, it makes NH4 plus. So when we subtract this, we have, so that's what we added. So now after we subtract it, we have 2 times 10 to the minus 3 of our base left. We don't have any acid left because all of our acid reacted with our base. So we have no acid left. And then left over here, we have 5. Oh, I don't mean that plus there. We have 5 times 10 to the minus 4. Now look at what we've got left here. Right? Huh. And so when we look at this, and again, you didn't need to keep the CL here. You could have just done this too. It's whatever. You could have done it 100%. You could have just done a net ionic on here. Whichever one makes your brain happier is fine with me. But look, it's a conjugates, right? So we can use Henderson-Hasselbalch here. Okay, so I'm not going to give you the shortcut to Henderson-Hasselbalch yet. We're going to do it the long way. You need to find the new molarities here. I just put big M for molarity, right? So this is a problem that people had with the quiz. You forgot this piece here. What do I mean by this piece? We had 25 milliliters in the beaker. We added 5 milliliters. That means our new volume is 30 milliliters, right? So this molarity is going to be 2 times 10 to the minus 3 over that's just how I go to liters easy. I just multiply it by 10 to the 3. However that makes you happy is fine. So that gives us, what is that, 0.0667 molar. This one doesn't matter. Our NH4Cl is going to be 5 times 10 to the minus 4 over 30 times 10 to the minus 3 liters. Just going to put moles here so you remember. So this new molarity is 0.017 molar. Right, then we can just use our Henderson-Hasselbalch. And you can use Henderson-Hasselbalch, I don't know, you can either use it with your pKa or your pKb, whichever one you're happier with. Just make sure if you use it with pKb, you switch it around. And yeah, so Avanish just pointed out, so with Henderson-Hasselbalch, I just don't want to confuse you on this. With Henderson-Hasselbalch, because you're dividing them both by the same volume, and when you do your Henderson-Hasselbalch, pKa plus log of NH3 over NH4 plus, or NH4Cl, however you want to do this. Technically, you have molarity in here, right? But technically, we have molarity in here. But since we're dividing them both by the same liters, you can do moles in Henderson-Hasselbalch. It's not, you're going to try it. You will get legitimately the exact same answer. So if we do this, and I'm just going to do it with pKa because I've already done this with pKa. So if we do this with the pKa, we have, what is it, 9.25. So how did I get this? I just took 14 minus this, and that gave me 9.25 for my pKa. So 9.25 plus the log of our NH3 0.0 over NH4. Or you could have done this. Log of our NH3. You're going to end up with the exact same answer. This one, I'm just doing this with moles. This one, I just did it with molarity. But no matter what, you end up with the same answer. Again, this only works. The reason I'm always kind of hesitant to, oops, sorry, you get 9.84, by the way.
Professor, I had a question.
Go ahead.
When you got the new molarity, where did you get the 30.10 to the negative third liters from?
Such a great question. Because when we started, we had 25 milliliters, but then we added 5 more milliliters.
Oh, so then it would be those two added together to get the 30.
Yes.
Oh, okay, makes sense.
Yeah, and this, by the way, that was one of the most commonly missed questions on the quiz, just forgetting to add it. Yeah, so great question. And again, when you're using Henderson-Hasselbalch, you can use moles. You don't have to use molarities, but when you're using an ice table, you must use molarity. Okay, so I hesitate to tell you about the mole shortcut now because, again, I don't want you to think you can put it into an ice table. Ice tables must have molarities. Henderson-Hasselbalch, you can cheat a little there and just put in moles. It works the same way no matter what. So you try them both, you're going to get the same answer no matter what. And again, now, remember at the beginning of this problem, we said we just added a little bit of HCl, right? We added a little bit of HCl to our beaker of our ammonia. So our answer should still be basic, right? It should definitely still be pretty basic. And indeed, it is pretty basic. Okay, so I know this is kind of a mess here, but any other questions on this, by the way, before I change this? Any other questions? I know my mole table is not very pretty, but.
Can you put where you have it kind of typed out so I can read it a little bit better?
Yes, I'm going to do that. This is what I was hesitating before. I don't have it in the same order here when I typed it out. So see how this goes NH3, HCl, NH4? I have this switched. So make a note that it's not written out the exact same way. These two columns, when I typed it, I'm not sure why, I flipped these two columns. It's still correct, but I just don't want you to get confused with that. So I'm going to show you it typed out, but I have to delete this to do this. So here it is all typed out. But again, do you see how I put NH4Cl here and then HCl over here? When I wrote it, I flipped it. So
it doesn't matter if it's flipped or not? Because that's what
no, not at all.
Oh, okay.
No, it doesn't matter at all. I just don't want you to go, wait, why did the number change from one to the other? It didn't. All these are still here in the exact same places they were before. I just flipped the two columns. Because all that matters is you know that this is NH3 and this is NH4Cl. Here it is much prettier though, right? So much prettier. And again, you could have put these in here. You end up with the same thing. Because here we're dividing them both by 30 milliliters anyway, which ends up canceling each other out when you put it into your fraction over here. Okay, so now this is before equivalence point. How did we know we were before equivalence point? We knew we were before our equivalence point because number one, we found out how many moles of our base we had. When our moles of our base equals our moles of our acid, we are at our equivalence point. When we found out our moles of our acid, we were at 5 times 10 to the negative 4, which is less than this. So therefore, we were before our equivalence point. Before the equivalence point, we ended up with a Henderson-Hasselbalch because we had our weak base and our conjugate acid. And again, if you don't want to put this, you could have just done it like this too. Whichever one you want is fine. Okay, so now what about the next one? Now I want to know what the pH is at the equivalence point. So remember, we found out this is how much NH3 we originally had. So that means we're at our equivalence point when our HCl is also that number of moles, right? So when the base equals the acid, we are at our equivalence point. So we will be at our equivalence point when we have 2.5 times 10 to the negative 3 moles of HCl. So that's when we're at our equivalence point, when we have that much HCl. Okay, so now if we want to know, hold on, sorry. So if we want to do this, how much HCl did we add? So if we have 2.50 times 10 to the 3 moles of HCl, how much HCl is that? Well, this is like a 209 problem, right? 2.5 times 10 to the minus 3 moles of HCl, right? And our molarity is 0.1 molar. So 0.1 moles of HCl in 1 liter, right? And then, I mean, we'll go to milliliters. In 1 liter, there's 1,000 milliliters. 25 milliliters HCl, right? This is like, we did this in like intro chem, right? So that's how much HCl we're going to need to add to our beaker to get to our equivalence point. So we need to add 25 milliliters of our HCl to our, oh, look at that, ends up being the same. That's just chance. I didn't intentionally do that, to 25 milliliters of NH3. Again, that was complete coincidence that they're the same. Okay, I think I have this written down here. Oh, I do. There it is. This is the exact same thing. Okay, so we added 25 milliliters. And the amount of moles, again, if we added 25 milliliters, I said the word added, that means we're going to do a mole table. Added means moles. Got to do a mole table. So here's our moles of our NH3 we start with. Here's our moles of our HCl that we start with. So we're going to add HCl, and it's going to make NH4Cl. Okay. So someone asked a little question here. Can I use the M1V1? That only works if it's a 1-to-1 ratio, and I wouldn't do that because sometimes it works and sometimes it doesn't. Okay, so now for this question, we have to figure out how much we've added. So if I do my moles table, so if we have NH3, I'm just going to make this bigger right here. So if I have before, and we have NH3, HCl, and H4Cl. So before, we have 2 times 10 to the negative 3. And 2 times 10 to the negative 3, because they're the same, because we're at the equivalence point. Okay, now our change. So this is going to go down. By the way, I forgot the 5, sorry. It's 2.5, right, 2.5. So going to go down by 2.5 times 10 to the negative 3, right? This is going to go down by 2.5 times 10 to the negative 3. This is going to go up by 2.5 times 10 to the negative 3. So in the end,
Professor?
Yes.
This is kind of where I got stuck. How do you know when it's going down and when it's going up at this point?
Okay, so how to know if it's going down or up at any point is you have to look at your balanced chemical, your equation. So that's going to be your guide to who's going up and who's going down. So we started with 2.5 of this and 2.5 of that. If we add this and we add this, they both go down, but they make that. So that's how we know that this goes up by this amount. And we're going to be doing a lot more Le Chatelier's today, but it's all like reactions in Le Chatelier's principle. So this is how you know this goes up, because when we add this and this, they react to form this.
Okay, thank you.
And then we'll do some more Le Chatelier's to help you with that, with when we're at like the buffer pieces in a little bit too. So that means we have none of this, we have none of this, but we have this. That's what we have in the end, right? Now, if we want our new molarity, we have none of this, we have none of this. But remember, this is going to be 2.5 times 10 to the negative 3 moles over, what's our volume? Very commonly missed here. Is it 25 milliliters? It's, so I see some in the chat. Yeah, it's 50 milliliters, right? So it's 50 milliliters, not 25 milliliters, because we had 25 milliliters and we added another 25 milliliters. So now we have 50 milliliters. So
Why was another 25 milliliters added?
So, because it asked for the calculate the pH at the equivalence point. Oops. Mm-hmm. So calculate it at the equivalence point. And so at the equivalence point, we know that we need the same amount of moles. Then we used that moles here to figure out how much HCl we had to add to get to our equivalence point.
Oh, so it's not always going to be 25 mLs there.
Yeah.
That's a coincidence. Okay.
Yeah, coincidence, which I wish I wouldn't have done, because then, yeah, so it's not always 25. It's very rarely the same, but this time it just somehow ended up being the same. So okay. So the key is when you're at the equivalence point to figure out what this new number is.
So anytime we're at the equivalence point, we're going to always be adding another amount of milliliters.
Mm-hmm. And how you find that is you know that the original moles, whatever you started with the original moles, that's going to be your new moles. Then you have to do a little stoichiometry calculation here to figure out how much of it you actually added. So when we have this many moles, it ends up being 25 milliliters of HCl. Okay. And so when we do that, that's like what? 0.05. Yeah. 0.05. I always just put times 10 to the negative 3 and just leave it liters, because this came from 25 milliliters plus 25 milliliters, right? Again, most commonly missed piece on the quiz. This little baby bit right here. Okay, so then when we do that, our new molarity is 0.05. I'll worry about my sig figs in the end. Molar. Okay, any more questions on this piece? Because we're not done. We just figured out, oh, we have this as our conjugate acid. So if we only have our conjugate acid in water, we have a whole nother piece. So let me just erase this and I'll show you this meter again. I think I have my ice table flipped again, but same thing. So here it is again, meter. But now all we have is the molarity of our conjugate acid here, which means that at the equivalence point, we're going to have to do an ice table with the Ka of our conjugate acid. So this is a moles table. Whenever you add anything, moles table. Now, because we're going to have to do an ice table, we must use the molarity. You cannot use the moles in an ice table. Does not work, right? Because we're squaring things and it will not work there. Okay, so next piece. I put these little yellow things here, just like I had in the other videos, to help you kind of see where we're going and what we're doing. So when we're doing this piece here, the pH at the equivalence point is determined by using the Ka of the conjugate acid. So we've just determined our molarity, which was 5.05 molar, right? And this is our overall reaction. But now again, all we have is this in here. So if this is all we have, our NH4, remember Cl comes from a strong acid, so we ignore it. So we have NH4 plus. So when you put NH4 plus in water, we make, right, this is an acid, that means this is our base. Acids lose, right, bronzide lowering, bases gain. So our ice table, I'm going to make a really big ice table. ICE. Our ice table, I'm just going to ignore my water because I don't need it. When we do our ice table here, we have our NH4 plus, which is 0.05. And we don't have any NH3, and we pretty much have no H3O plus. So when we do this, our NH4 plus is going to go down by X. This is going to go up by X. This is going to go up by X. So this is going to be 0.05 minus X, X, X. This is an acid, so we need to have a Ka. Our Ka is going to end up being, right, X squared over 0.05, because I'm going to assume my X is small. Problem here, this, again, this is a problem, this is a mistake, a very common mistake. This is we were given a pKb, but this is an acid. So I need to change my pKb into a Ka. Right, so we got to change the pKb into a Ka. So when we do this, 14 minus this, that's going to give us our pKa, which is 9.25, right? This is our pKa. And then to get from our pKa to our Ka, right? Actually, I have this written here for you. I'll just put this on here. Okay, so before I do this, because I'm going to erase this so I can have more room. Any questions on our ice table? Right, this is the ice table we've done now like 15 times. Well, no, like 30 times.
Is the ice table gonna appear when you like go to the next part?
Yep, that's why I'm gonna erase it now.
Oh, okay, okay.
Okay, quick question.
Oh, shoot. Yeah.
Oh, no, you can erase it. You're fine.
Oh, okay.
It doesn't really have anything to do with that.
Okay, go ahead.
More curious, why are you changing from pKb to pKa? Like what's the, why?
Super great question. Because if you're doing an equilibrium expression with acids, you have to be using Kas or pKas. If you're doing an equilibrium expression with bases, you have to be doing pKbs or Kbs. Because this here, so what we're talking about is a conjugate acid. When we write our equilibrium expression, this has to be Ka.
Oh. So why does it give us a pKb?
Right, because we started with a base in the beginning.
Oh, and now it's the acid.
Now it's an acid. Yeah, so that's probably the second most common thing is when we kind of go through the titration, you have to keep an eye on, am I an acid or am I a base? Because if you're an acid, it has to be a Ka. But if you're in a base, then it has to be a Kbs. And so that's why this little equation, is going to be so important to know. I've got a conjugate acid here. This must be a Ka. Any more questions on that? Good questions, because these are going to come up. They come up again and again and again. And when you watch the supplemental video that I made, I go through this and specifically address the exact, not the exact questions, but almost the exact questions from the lecture quiz.
So the initial you got from the new molarity, right?
Mm-hmm.
Okay.
Yeah. This came from the end of that moles table on the last page, from the new molarity, because we added the 25 milliliters of this,
yeah,
and the 25 milliliters of this, and then we ended up with that. I can't remember.
Because the whole point of a moles table is to get that new molarity for this ice table, right?
Exactly. Yes. That's the point of the moles table, yes. Okay, so again, they gave us the pKb, so we had to get that into a Ka because all we had was acid here. So we had our conjugate acid. Again, that's why these conjugate acids and bases are so important for us to remember. So then it's just x squared, x is small. If we look at our Ka, it's 10 to the negative 10th. Our original concentration was 10 to the negative 2. X is small, definitely going to work. Difference of a magnitude of 8, there is no question. I'm not even going to check it. I know it's going to work. So then when we get our X, knowing that this here is a conjugate acid and that this is a weak acid ice table, that means our X is our H3O plus, so we can just take the negative log of it and be done. So when you're doing these things to watch out for, you need to know what reaction, when you're doing your ice table or your moles table, you have to know what is kind of the governing reaction of your problem. At any step, you kind of got to know, what am I doing? Because you need to know what the identities of these are. So many times I see people put an ice table, but there's nothing written here. I do not know how you keep track of what these things are if there's nothing written. I literally couldn't do it if I tried. You have to know what these are. Otherwise, you have absolutely no idea what we're solving for. I mean, how do you even make this? And how do you know what this is if you don't know what these are, right? And the only way you know what these are is because you understand how to write the reaction, right? Next piece. Since you know this is an acid, that must mean when you write your equilibrium expression, you have to have a Ka here because this is a conjugate acid. So this must be reflecting that acid. Because it is an acid, that means that your X is H3O plus, so you can just take the negative log of it. No need to subtract from 14. Okay, and again, this is kind of the conceptual thing. At the equivalence point, all of the weak base has been converted to the conjugate acid. And so all we have now is conjugate acid sitting in water. Okay, any questions on this one so far? Because of course, we can't be done yet because this was just at the equivalence point. What about after the equivalence point, right? So now we know that from our last problem that 25 milliliters was the equivalence point. But let's say that this was a separate problem and we didn't know that we were at our equivalence point at 25 milliliters. How do we know we're beyond our equivalence point? So what we would do is we know that at our equivalence point, we're at 2.5 times 10 to the minus 3 moles. So we would find our moles of our HCl, right? So if we've already added 30 milliliters of our HCl, we would find that we're at 3 times 10 to the minus 3, right? Now, how do we do that? Let me just go back here. That's not backwards. It's the same thing we did here with the stoichiometry, right? We're just going backwards on it. Okay, so we know we're beyond our equivalence point. So if we're beyond our equivalence point, then we look at our, again, we're adding. So we have 3 times 10 to the minus 3 moles. And again, I just did that using stoichiometry. I'm not going to use blue. I'll use red again. So if we have our NH3 and our HCl and our NH4Cl, and before we had 2.5 times 10 to the minus 3, and we added 3 times 10 to the minus 3 moles. We don't have any of that. Our change, this is going to go down by this. This is going to go down by that.
The 3 times 10 to the negative third, that's from the 30 milliliters, right? Oh.
Yes, yes. And then this is going to go up by that. Oops. So then when we subtract that out, we have, so in the end, we have none of this. We have, oops. Just, sorry, my pen is not working all of a sudden. There we are. 5 times 10 to the -4. I guess -4. And then we have 2.5 times 10 to the -3 of this. Okay, so now, if I look at these moles here, let's go, we have our identities. So we have a strong acid and a weak acid. So remember when we did strong acids and we did mixtures of acids, remember if there's a mixture of an acid and there's like a strong acid and a weak acid, we literally just ignore our weak acid. That's literally what we're going to do because this is our weak acid. That's our weak acid. This is our strong. So we're only going to care about this. I'm not even going to like consider that. I'm going to be like, nah, don't care. It doesn't matter to me. But what's our new molarity? We got to find our new molarity. It's 5 times 10 to the -4 moles of HCl over our volume is 25 milliliters plus 30 milliliters. Right? That's our new volume. Sorry. I have this neater in a second, as you can see. 25 plus 30 milliliters. And then obviously you have to turn that into liters.
0.055 liters.
Yeah. So then you end up with 0.045 molar. Everyone knows how to turn those into liters. And then our pH is just negative log of, that's not my molarity. I just put this number here. Your molarity is 0.0091. Negative log of 0.0091, which equals 2.04. And this is what we would expect, right? If all we have is strong acid, our pH should be really low. I mean, we have a little bit of our weak acid here too, right? We have a little bit of a weak acid, but no matter what, we should have a very low pH, right? So we should expect a number that's going to be like low, like less than 3 for sure when we're done because we have excess acid. Now, again, why did we ignore this weak acid? Because remember, when we mix a strong acid with a weak acid, we only need to consider the strong acid. The weak acid's contribution to the pH is negligible. It's beyond our significant figure, so we don't even consider it. Okay, here's the same thing, nicer. I have it all typed out pretty-ish, right? And again, we just ignored this because it's a mix. So we only cared about this new molarity here. And again, on the supplemental video that I made to help you with your lecture quiz, I go through all sorts of different scenarios of titrations, all different ones, specifically addressing the things that relate directly to your quiz. Okay, any questions on this one? Good here? Okay, so now, what if you have a polyprotic acid? So if you have a polyprotic acid, I'm not going to make you do these titrations for a polyprotic acid, but just know that you can see it on a titration curve, right? Because there's 2 different equivalence points for like sulfuric acid. You can see the equivalence point when it loses 1 hydrogen and when it loses a 2nd hydrogen. So instead of just having a nice smooth curve with 1 equivalence point, you'll have multiple equivalence points. So that's how you can tell if you've got a polyprotic acid. Now, when we talk about our equivalence points and our endpoints and titrations, so when you in 219 did some titrations, we looked at the endpoint, and in 219 we used an indicator. We used phenolphthalein, right? So in your titration, it turned pink, right? So we're going to look at how these indicators work. So what the indicators do is they change color when we're about at those endpoints. So at that inflection point in our curve, they change colors. And so we're going to actually look at these. These indicators are actually they're just conjugate acids and weak bases. And so how do we monitor pH? We can either use a probe or we can use an indicator. So we're going to look at these indicators. And so a lot of dyes change colors depending on the pH, and they're usually going to be like weak acids with their conjugate bases. And so when I'm going to show you these, so this is just the indicator. So this is like HA. And this is like A minus. So just think of it like that. We're just using the number, we're just using indicator instead. And so the color depends on the mixtures of the conjugate base with the acid, right? So when they're about equal, when they equal each other, the colors mix. When the base is greater than the acid, it's going to be, again, a mix. And then, so we're going to look at these now. So I'm going to show you the actual phenolphthalein indicator that we've used. So here it is. So you can see here, here's the acid. So here's the A minus form. Sorry, not the A minus form, the HA form. And here's the A minus form. See, there's the minuses for our minus form. And again, when you get to organic, these will all make lots of sense to you. But right now, don't even worry about this. So when we're at our acidic, this one has no color. So you can see here's our pH. This is going to be, oh, can anybody tell me what kind of titration this is? So like weak acid, strong base, or weak base, strong acid, or strong acid, weak base?
I'm going to guess strong base.
Strong base and a weak acid?
Yes.
Any other guesses? Strong acid, weak base. I'm seeing a few. Okay, so how can you tell? And I'm telling you on your exam, I'm going to have you draw these. I'm going to say, hey, draw the titration curve for one of them we've done. So what can you tell? First of all, here's where you're starting. Starting at an acid. We're ending at a base. So we must be adding a base to our acid, right? And then we look at our titration, our endpoint. It's basic, right? So that's going to give you a hint. And I'm not going to tell you what you get here because this one's, you're going to see this one again later. Okay, so now, if this is an acid, it's colorless, but as in its basic form, it changes color, right? And so that's how we can tell when we're about at our endpoint. So this is another one, methyl red. This one has lots of different colors, right? And so depending on if it's at the acid form or the base form, it changes colors depending on, and that's how our indicators work. And so most of our indicators, they show different changes in their pH depending on where the endpoint is. So we always choose our indicator depending on where we think our endpoint should be. So how we do that is if you look at your pKa, it should be about when they're equal to each other. So if we look at this, I'll just show you some indicators just so you can see this. So these are all like a bazillion different indicators. So all you really need to know is that the indicators are changing color depending if they're acid or their base form. And the best indicator, so for example, if you knew that your pH, your endpoint should be like right around, let's say 5. Well, then you shouldn't use any of these, right? You shouldn't use this one. This one also wouldn't be helpful. That one would be helpful, right? Because you can see the color change happens around 5. So when you know where your endpoint is about to be, that's how you select what indicator you want to use, right? This again, none of these would be helpful because None of these would be helpful. So you would choose methyl red in this case. Okay, now, next piece we're going to talk about is solubility equilibria. So solubility equilibria is, remember when you took 219 or Gen Chem and you said something was insoluble? Well, it's still soluble. It's just barely soluble. So there's no such thing as insoluble. There's always a little bit there. So our solubility product is called KSP. KSP is just like every other K we've ever used, just SP for solubility. So again, if we look at our dissociation, so here's our insoluble compound, and it makes two products. And so our equilibrium expression, again, we don't put solids in there, it would just be our products. So for example, if you have PbCl2, so if PbCl2 dissociated, you have one Pb and two Cls. Remember, it's products raised to the coefficient. So our KSP here is going to have this 2 here. Now, we've been hanging on acids and bases in a while, and we haven't had any types of stoichiometry in these because it's always been just one we've talking about, right? So when you're doing solubilities, you're going to need to take into these into account now, just like we did at the beginning of chapter 14. So it's not new, it's just we haven't done it in a while. So these are some KSPs. So remember, if K is very, very small, it means it's going to, the equilibrium is going to lie very, 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 very far to our, look at some of these, to our reactants. So we say, for example, that lead 2 sulfide is insoluble. I mean, it is really reactant favored, but we still have some lead and some sulfide in there. So that's what we're going to find out. How much lead? How much sulfide? Right? Copper 2 sulfide is insoluble, but how much copper? How many copper ions on there? How many sulfate ions? Right? So that's what we're going to figure out with this, what we call molar solubility. So it is the amount of solute that will dissolve in amount of a solution, right? And so I think this little thing is kind of confusing, but we'll talk about it, how we do our molar solubility. It's just an ice table like you've done before. Just don't forget about the stoichiometry of it. So for example, what's the molar solubility of PbCl2 in water? We write our dissociation equation. So when we do our ice table, now I use S's for solubility. Feel free to continue to use X's for solubility. When we do this, we want to figure out what our molar solubility is. And so you can see this is our S, but this is 2S, right? Because of our equilibrium expression, right? So this is on our ice table. And when you write our KSP, we need to remember to square this. So the most common mistakes here, people forget both of those things. This is going up by 2 because of stoichiometry. When you do your K, you have to remember to square it or cube it, or whatever. So now, when we put that in, we have S times 2S squared, right? So we have our K, let me just go back here. So we have our KSP, right? And then we're gonna find our KSP on the table in just a second. The KSP is 1.17. Sorry, 1.17 times 10 to the negative 5. Again, this is from the table. And then we're just going to solve for S, and that's our molar solubility. Right? So we're just going to solve for our S now. And so you get 1.17 times 10 to the negative 5. And then so we have 4S cubed, divide by 4, take the cubic root. Here is our S. Right? Divide by 4, take the cubic root, and we get this. And this is the molar solubility of PbCl2. Okay, so I'm going to do another one of these. Exact same thing. I just want you to see this twice. I'm going to do it with PbBr2. So let's do this with lead 2 bromide. This time, we're going to try and find the KSP. It's the exact same thing. I'm just going to have my S already. So when we do this, write our dissociation equation, write our equilibrium expression, remembering, don't forget to square it, products raised to the coefficient over reactants, just like we did at the beginning of chapter 14. When we do our ICE table, I'm giving you S. This is S or X. The reason I changed it from S to X is because in our ICE tables that we've done throughout the last month, X has always been the change. This isn't the change. This is the answer, right? There is no change. It's the answer. So I changed it to S, but feel free to keep using X's if you prefer. So we have, this has gone again up. Don't forget this 2 here, right? Because of this 2 here, it goes up by 2 times this amount. So here's our new equilibrium. And so then if we're finding, go ahead.
For these ones, is it always going to go up?
Yes, because we're putting this in, we're putting our solid in, and then we're trying to figure out how much it's going to dissociate. So how much it's going to be. So yeah.
So then for this table, there should always be pluses, right?
Yes, because we don't include this in our table at all. And so we're just putting a solid in, and we're seeing how much of these are made. So yeah, these will always go up. They'll always be pluses when we're doing these molar solubilities. Yes, good question. And so now we have these answers here. Or we have these. Again, what we need to remember to do, square this one, right? This 2.1 times 10 to the negative 2 needs to be squared. Molar solubilities aren't very difficult. It's just these little pieces like forgetting to square it, right? That's what gets us sometimes. Or forgetting to multiply it by 2. And so here is our KSP, 4.3 times 10 to the negative 6. So this is really using what we learned in the beginning of chapter 14 when we started with equilibrium. So it's kind of good review because we've been sitting with acids and bases for so long. This is kind of getting us back to reviewing chapter 14 again. Okay, so now let's look at our KSP and relative solubility. So this is just a little note. You can't really compare KSPs to each other unless their stoichiometry is the same. Like, what do I mean? Oops. Like if you have, actually, I'll have to look at a table to show you this. I'll come back to this in just a second. Or maybe I won't. It won't go beyond backwards any further. Okay, well, I'm sure I've got another table here that I can show you. I don't. Okay, so I can't show you the table right now. But so for example, if you had like AgCl and PbCl2, both of these are insoluble. Now, I don't know their KSPs because I can't see the table, but if these KSPs were the same, you couldn't say that their solubilities were similar because when this dissociates into 3 ions. And this only dissociates into 2 ions. So they are not going to be equal. So the only time you could compare a KSP of one compound to a KSP of another compound is if they dissociate into the same number of ions. Does that make sense? So you could, I don't know. I'm trying to think of another one that you could do. Another one that had 3 ions or 2 ions, like PbBr2. You could compare these two. And then you can make some assumptions, but they have to dissociate into the same number of ions for you to compare one KSP to another KSP. Okay, now the common ion effect. We've actually talked about this common ion effect before. So if we add a soluble salt that contains the ions of the insoluble salt, it will decrease the insoluble salt. So I talked and you're like, what? Okay, this is Le Chatelier's principle. So let's look at this. So for example, if we have PbCl2 and I add So when it comes apart, it comes into PBs and CLs. But if I add NaCl, it's going to shift this way, right? So it's going to decrease the solubility of PbCl2, right? So this is the common ion effect with solubilities. And we can actually calculate this. Okay. And again, straight Le Chatelier's principle. So calculate the molar solubility of CaF2 in a 0.1 molar NaF solution. So we have our insoluble CaF2, but I'm adding, again, Na, don't care, this common ion. I'm adding this common ion to it. So here it is, and I'm going to add this, so it should make it less soluble. So our KSP is going to be Ca times F squared. You know how to do that. So what we're going to do is we're going to start with, in this case, we're going to start with this amount. So instead of a 0, we're starting with this from our NaF. And again, this is going to go up by 2s. It's going to be S. And so in the end, we have 0.1 plus 2s. And you can probably already guess what we're going to do. We're going to assume this is small because our math would be awful without it. So this is an ice table just like we've done before. So there's our table. I'm going to assume this is small. So then it's just going to be 0.1 squared. And now I need to have my, again, this would be given to you. It would have to be given to you here. In this case, it is 1.46 times 10 to the negative 10th. Then we just divide by 0.1, divide by 0.1, take the square root, right? And then we get, this is our molar solubility, 1.46 times 10 to the negative 8. Okay, so now one more fun one. We're going to do these molar solubilities. Determine the concentration of silver ions in seawater that has a chloride ion concentration of 0.55 molar. And then I got to give you, here's your KSP of AgCl. So I want to know, what is the concentration of silver ions in seawater? And seawater has, here is the concentration of Cl ions. And then here's the KSP of AgCl. I'm just going to put that in my brain, 1.77 times 10 to the negative 10th, because we're going to need it. So here is our equation, right? And we have 0.55 molar of this. We want to know what's that, right? So when this is 0.55, what is our Ag? And it was, right, our KSP, 0.77 times 10 to the negative 10th. So we just make our ice table, just like we did before. And again, we're going to assume this is small. So then we're going to have our plus S plus S. We're starting with this amount. Same thing, sorry. But now I lost my KSP. So it's just S times 55, assume this is small. Right, and this is 1.77 times 10 to the negative 10th. So you just divide it by 0.55. And that gives us our new solubility. So these ones, not so bad. So this is the concentration of our Ag plus in seawater. Okay, so now, pretty simple. These ones aren't so bad. So what about how pH affects these insoluble compounds. So specifically when we talk about like hydroxide, so most hydroxides are insoluble, and this directly applies to what we talk about in lab. So we have an insoluble ionic hydroxide. The higher the pH is, the lower the solubility of the ionic hydroxide. The lower the pH, the higher the solubility. Why? Because when we look at this, if you increase the pH, it's going to shift it over here, right? Which will make it more insoluble. If you lower the pH, which means we have lots of H3O+, the H3O+ is going to react with this, which decreases this, which will shift it towards our products, right? All Les Chateliers here, 100% Les Chatelier. So let me say that one more time. If you increase the pH, it's going to shift it over towards the insoluble side. It's going to be reactants. If you decrease the pH, which means adding H3O+, the H3O+ is going to react with this, decreasing our product, making it shift back over towards our product. Now, same thing happens, well, sort of, the opposite, I guess, same principle, opposite effect. For insoluble ionic compounds that have anions of weak acids, when you lower the pH, the higher the solubility. Now, again, actually same thing. Here it is right here. If you have this, if you add H3O+, this is going to react with this, which is going to, again, increase our solubility. And I actually wrote this here. Here's what happens. And it actually increases our solubility. So this is why in lab, it'll say like, make it alkaline or make it acidic, right? And you'll have to test, because what it's doing is it's actually trying to shift it over towards the precipitate sometimes, or sometimes it's trying to shift it over towards the solubility, right? And so it's actually, and you're going to see one where you can high pH and low pH, and you can get a solid both ways. Okay, so now precipitations, when we've done precipitations before, precipitations, we learned about those like saturated, unsaturated, supersaturated, right? In 219 and maybe even in 209 or intro chem, depending on where you took it. This goes back to Q's and K's. So again, great review for your exam, Q's and K's. Q means at any point in time in the reaction. K means at equilibrium. So we don't know, we have to, remember we developed a way to figure out if it was going to shift towards the products, reactants, or be at equilibrium. Remember, if Q equals K, that means we're at equilibrium. That's going to be a saturated solution. It will not precipitate. If Q is less than K, the solution is unsaturated, right? That means it's going to go towards the products. So I'm going to get you a little reaction to look at. So if Q is less than K, right, that means it's going to continue in the forward direction and there will be no precipitation. If Q is greater than K, that means it's going to shift back towards our reactants and we're going to see a precipitation. Now a supersaturated solution, these ones are really fun. I'll show you a video of this one too. Okay, we don't really have time to do our next one. So I think that we'll stop there. Someone asked a question.